So welcome everyone. We are from the HungaroMet, so the Hungarian Meteorological Service, and I am Marton Pall. I graduated from Eötvös University in 2021. My thesis was about the comparison of lightning activity of supercell and non-supercell thunderstorms, but it's not the point now. I've been working at HungaroMet since November 2021 as a general weather forecaster, and I have also been performing several weather warning tests for 1.5 years. And I have also been on Hungarian public television as a weather forecaster since April this year. But now let's get to the point. I've prepared a case study, and I'd like to talk about, this may come as no big surprise, Cyclone Boris. I assume that all of you listeners are aware of the terrible weather conditions, and some of you may also lived the terrible weather conditions in Central Europe caused by this cyclone. And that is exactly why I want to present not only facts and figures, but I also interesting facts and reports. So this is not your typical case study, and for understandable reasons, I will concentrate mainly on Hungary. Yes. Okay, so in this infrared satellite image or satellite loop here below, you can follow the whole life of Boris. The formation of the cyclone was preceded by a cold front that arrived in the region on September 11th. The congestion of moist air ahead of the front and the cold ice behind the front and the associated jet stream showed the beginning of a normal marked cold frontal intrusion. Reaching the Alps, intense lee-side cyclogenesis started on September 12th on the southern side of the mountain range. The front itself slowed down, the cold core at the high altitude caught up with the front, and intense precipitation started in Austria, Slovenia, and northern Italian areas. In the following days, the front stopped moving. Several waves were generated, and a vortex named Boris was formed, which soon showed the closed flow pattern even at the jet stream altitudes. After that, the cyclone barely moved, but continued to deepen. The moisture precipitating in the winding arms of the cyclone provided a steady supply of precipitation, which fell most intensively in the northwestern part of the vortex, where the flow also boosted by the Alps. On the 17th of September, the cyclone began to fill, and the high-pressure cold vortex moved over northern Italy, causing more significant rainfall and flooding. So we should start with the dry but meaningful facts. The most severe situation was in lower and upper Austria, where rainfall of over 300 millimeters was recorded in larger areas, as you can see, accompanied by strong or gale force northerly winds. The cyclonic precipitation system arrived in Hungary in several waves, with 50-60 millimeters in the Great Plain and up to 100 millimeters in places in the western Transdanubia. On the back of the cyclone, wind gusts of more than 100 kilometers an hour occurred in the Lake Balaton area. The cyclone also caused a significant drop in temperatures, with maximum temperatures above 30 degrees Celsius being replaced by temperatures of just over 10 degrees Celsius. The heavy rainfall associated with the cyclone caused extreme river flooding in the Danube, storm damage at Lake Balaton, and also collateral effect. The sudden cooling during the bird migration caused mass bird mortality. Quite astonishing amounts fell in just 4 days in Lower Austria, The 371 millimeter in Lilienfeld is the equivalent of about 3/4 of a year's rainfall in Hungary. So it's quite amazing. Here, the rainfall was not even close, with 184 millimeter falling in Bakonybél, Hungary, by the morning of 16 September. Up until the morning of 15 September, so you can see this, an unprecedented flooding situation was caused by exceptional rainfall of more than 150 millimeter in 24 hours over large areas, mainly in lower and upper Austria and southwestern Poland. The cyclone brought with one of the biggest temperature difference ever in Hungary. You can see here, while in Sopron, it rained continuously at 6 degrees. With a storm northerly wind, thunderstorms arrived in the eastern part of Nyírség, and before that, the sunshine caused temperatures reached to 30 degrees in Szamosújra or Milota. And this map also illustrates what I said before. In the western part of Hungary, the deviation of the maximum temperature from the climatological averages was mainly around -14 or -15 degrees Celsius, while in the northeastern part in Hungary, the temperature anomaly was +5 to +6 degrees. It's quite amazing. And in the addition to the exceptional precipitation caused by the cyclone Boris, the winds associated with the squall were much less severe, if I can say it. More significant windstorms developed in the northern Transdanubian areas and in the Lake Balaton region, as the western part of the country moved into the back of the cyclone, where a significant pressure difference developed. On 14 and 15 September, a wind tunnel was formed with gusts of around, you can see here, 90 km/h in several areas. The strongest wind gusts were measured by instruments at higher altitudes, with a maximum gust of 131 km/h on Kap Hill, breaking the daily Hungarian national wind record. Gusts of 105 km/h were recorded in several areas around Lake Balaton. And I mentioned that I would like to talk about interesting facts. Now comes perhaps the most exciting calculation. So let's get back to the 7-day precipitation sum map. Zoltán Goda, an assistant professor at the Faculty of Water Science at the National University of Public Service, has calculated, using artificial intelligence, approximately how much water could have fallen from Boris. So the method was simple, but he had to use AI. So with the help of AI, he laid a grid of 800 squares on the map and estimated the average rainfall values based on the colors of the squares. He did this for each square, adjusted the averages by the numbers in each square, and from there it was easy to calculate the total. Of course, this is still only gave an approximate value, so it's of course not the exact value, but it's enough to at least give an order of magnitude. The result was quite shocking for me because Boris left behind approximately 35 to 50 cubic kilometer of precipitation, and that's only a single Mediterranean cyclone, and it's also equivalent of the Lake Balaton. So but Lake Balaton 21 times the Lake Balaton, which is the largest lake in Hungary and also in Central Europe. So it's unbelievable. And another interesting fact: Some of you may have come across the conspiracy theory circulating on Facebook, which incidentally gives a very accurate receipt for how the cyclone was made. So some people said that this cyclone was made, but let's see how is it possible? The recipe is this: 15 centimeters of water from the Black Sea was evaporated over a surface area of 40,000 square kilometers. And this is how the cyclone got its moisture. Now, this claim made me so angry that I did a calculation of how much energy this represents. The surface temperature of the Black Sea at the time was about 24 degrees Celsius. With the data just given, the energy required for the evaporation is 1.3 multiplied by 10 to the power of 19 joule. And that's a huge amount of energy and can be compared to various high energy processes. So I brought you some examples to give you an idea of the magnitude of this. For example, we can compare it to the energy of nuclear bombs. The energy released from the atomic bomb dropped in Hiroshima was about 63 terajoules, which is, well, quite a big energy. But if we compare this to the calculated energy release, we get that this equivalent to the energy of 215,000 atomic bombs. So like Hiroshima, it's quite big. But we can also compare it to the world's annual energy consumption, which is in 2021 was about 600 exajoules. And the calculated energy amount is about 2.26% of the total annual global energy consumption in 2021. And we can also compare it to the energy of earthquakes. The energy of a strong earthquake is, for example, a magnitude 9 earthquake is about 10 to the power of 18 joule, which means that the calculated energy is about 13 times of the energy of such huge earthquakes. And now I'm passing the mic to Adam.
Welcome, everyone. Practically, the introduction slide is almost identical to my partner's, but I introduce myself. My name is Adam Kokai from the Hungarian Meteorological Service, where I have been working as a weather forecaster for 3 years. I also manage the social media platforms for HungaroMet, where we create daily weather forecast videos for the company's YouTube channel. Additionally, we write posts and articles. The world of media is not new to me, as I have been working as a weather presenter for the Hungarian RTL television channel for the past 1.5 years. I am such an avid fan of the profession that I even set up my own weather station in my parents' garden in the countryside. I won't prolong the discussion. Let's turn to the weather situation of the continent. The weather across most of the continent doesn't hold many surprises, with a large-scale anticyclone being the dominant feature, centered over the middle of the continent. Cyclones and their associated weather fronts are located in the western parts of Europe, in the north over Scandinavia, as well as along the eastern fringes of the continent. As a result, most areas are experiencing sunny and dry conditions, but since we are already nearing the end of October, misty, foggy, and overcast regions are naturally occurring as well, so the inversion increasingly playing a significant role. The apparent path of the sun is getting lower, meaning vertical mixing is weakening, and as a result, the low-level cloud cover formed overnight does not dissipate everywhere. However, in the region of Italy near the Adriatic, we can also observe a lot of clouds and even some precipitation, which I will discuss later. In the anticyclonic flow system, milder than average air flows over most of the continent, which stabilizes the atmosphere. This is favorable for fog formation. As I mentioned, I also manage social media platforms where we create content that is humorous and funny, yet still maintains a professional perspective. On October 23, a cold front was caught in a squeeze between two anticyclones. The majority of the frontal cloud cover got stuck outside the Carpathians, but at ground level, colder air sipped with the northern wind, lifting the milder air present in the basin, which led to the formation of low-level cloud cover due to the condensation. And now I would like to return to why there was so much cloud cover in the Adriatic region. Well, ahead of the cold front, a weakening warm conveyor belt extended into the area, and the remnants of its cloud cover remain. This led to rain and showers, as the flow on the western edge of the anticyclone was southerly, pushing the moist air against the southern foothills of the Alps, causing the air to accumulate. Finally, I would like to conclude the briefing with an outlook. Is there any indication of a wintry turn in the forecasting models yet? It seems that anticyclones are currently strongly associated with Europe, as high pressure will continue to dominate most of the continent for the remainder of the month. Since the anticyclone extends from the ocean or settles over the interior of the continent, a wintry turn in the weather is not expected for now. The fronts will pass far to the north. Thank you for your attention.
And now Ivan Smiljanic is here to talk to us a little bit about the MTG FCI imagery.
I won't show too much imagery, but I will show you how much there is in one image or in few. Just to show you, advertise a little bit the Eumetview as a tool, but also new and freely available FCI data. So my name, you've heard, part of the EUMETSAT training team, and this is what we do lately. We try to understand this data. It's a new data, new products like this True Color RGB for MeteorSat users, at least. And I'm just going to analyze a little bit of this situation this morning or today with prevailing high pressure over the Central and Eastern Europe and the Rossby wave actually kind of moving from southwest to northeast, central, center of low pressure system being south of Ireland. This low pressure will actually not move more towards the west in the coming days. It came from the west, but then it hit the high pressure in the middle, and then it will actually move southwards from here. So under this condition, most of the central and actually eastern northern Europe below this polar front is stable, and you can see vast number of big patches of white clouds and potentially maybe snow. I had earlier briefing and I asked if this white thing over Finland is snow. Well, as this is True Color RGB, it tries to mimic whatever our eyes are seeing, placing the wavelengths or the beams of the RGB as our eyes would interpret. So we're using 0.6, 0.5, and 0.4 channel on RGB respectively, beams. And none of these channels have actually power to resolve the microphysics or the phase of any clouds or any water phase. Meaning you cannot know what is the low cloud, high cloud, or water cloud versus ice cloud. And you cannot even say what is a snow patch, what is a cloud patch, because for our eyes, if you look from distance, if you would be flying from an airplane, it could be a stratus cloud all the way down, or snow patch, and you wouldn't know actually without consulting different spectral regions. I'll come to this True Color RGB. So now I will switch to something that will tell us more about the systems we're looking at, the clouds we're looking at. Of course, for us meteorologists, synoptic situation plus maybe the distribution of clouds, orography, etc., gives us contextual hint on what the clouds are made of. Phase, are they vertically developed, are they active or passive, or they're dissipating, or it will build. However, from the satellite imagery itself, we don't get the information on the cloud phase per se, or the particle size. So for that, we need to move to, for instance, many other different Severi products, but also I will advertise here this cloud phase RGB, which is actually kind of a boosted version of natural color RGB. Why boosted? Because natural color RGB would give you in cyan shades the ice clouds. In white, it would be water clouds. Here, blue is kind of cyan blue is still ice clouds, and water clouds are in purple, pink to yellow, depending on the particle size and the thickness as well. So why do I say boosted? Because aside from better resolution, much better from 3 to 1 kilometer, you also get the better discrimination between the cloud phase. So the areas where you have water turning into ice, they're better discriminated, especially along the fronts. And also you get the particle size information. So the whatever is blue is ice, but you can have big ice particles, like here west of Sardinia, a small patch of deep blue. This is probably older cell that grew 2 hours ago, and then the ice crystals, they grew all together by now, and they are deeper blue. However, this one is more pale blue, meaning that the ice particles are smaller, and perhaps this is more active cell. In a similar sense, when you go from purple to yellow, you change the particle size. Deeper purple is actually bigger particles, water particles, and lighter to yellow is smaller water particles. And so you see here, Finland is not on the snow cover. However, there is some snow. So south, west Scandinavian mountains, you see some patches of snow, and also towards the north there is a snow. Turkey and towards the east as well. They usually show in the deeper, very deep blue shades. However, you can even see the different shades of snow depending on the ice crystal size, and this depends if it's melting, if it's high up in the mountains, etc. So a lot of information. I could talk much more about what we're seeing here. I will focus on, however, on two more things. And before focusing, I will move to something that we were used to see, and this is natural color RGB. And this week I was actually studying shadows. Believe it or not, I spent many hours looking at shadows, and I will just briefly give you some hints why is that the case. For once, we will focus here on the front in the northwest, and just by observing this front, you as a meteorologist, you can have a better understanding how high these clouds are, what the shape and form is, what are these clouds actually looking like a pixels to probably normal human couple of pixels here and there, patching. Not much real in-depth view over what's happening. There is kind of a shadow here, some shadow in these filaments along them, but nothing spectacular. However, if we move to, for instance, True Color RGB, it's much different story. So I'll toggle once again. And if you see this small cumulus, towering cumulus, maybe clouds behind the front, they start to have a shape. They are not pixels anymore. Really cloud-looking patches with almost in-depth view with the shadows and everything. Especially if you talk about this front, it becomes very apparent what the shape of the front is and what these cloud structures on top look like. Why is this important? I don't know. For instance, transverse cirrus clouds. You can see them very well, especially I have to say this is far towards the north, actually towards the edge of the view of METEOSAT third generation. So it's quite spectacular already. But it's all this interplay of shadows and cloud structures give you almost a 3D impression of the clouds. And also look at these snow patches over Scandinavian mountains. If I toggle between the two, okay, there is a cyan color indicating ice crystals, but the shape, well, is questionable. Here you almost can see kind of a mountain orography distribution in the region. So, and also some wavy clouds, Lee clouds probably, etc. So pretty interesting. And shadows. Okay, so there's a big black shadow here with almost red edges around here, and you have a blue shadow. And if you really zoom in here and try to understand this shadow, you see there is a break of the shadow here, and then it starts again. And you finally see that there are actually 2 layers of clouds, actually 3, low, mid, and maybe highest reaching vertically developed clouds. And then there is a front on top of everything. So that's one thing, the shape of the shadows. And it's quite, you see, it's quite abrupt gradient here. Whilst here over these clouds, it's more blurry, meaning that the clouds are getting gradually thinner and thinner. And of course, there are different colors. Obviously, one is with no clouds below, that's one thing, and the other has clouds below and it's blue versus black. And all these colors, they tell you a story. And I'll come to that as well in a moment, showing maybe just one more feature from this morning. These are these convective clouds. Okay, we may go to maybe natural color RGB and go to a little bit earlier moments, because for convection, the best time is to observe is morning hours. Why? Because you then see better topography of the cloud tops because of the interplay of shadows and the structure. So this is the cloud in the morning, convective. Okay, it's blue, it has some kind of shape, and you could say, if you're a meteorologist, pretty round, it's a convective cloud. Otherwise than that, there is not much more information you can fetch from here. However, if we move to, for instance, True Color RGB, right, now you start to see some real structures on top of these clouds. And I think I missed it somewhere. There was some very nice looking cloud. Maybe a bit earlier we can even go. Oh, that's too early. A little bit later, just give me a few more moments. Yeah, anyhow, you start to see really defined structures on top of these clouds. And if I zoom here, I think it was around about here where I was also investigating a little bit the shadows. You if you really zoom in, you start to see shadows being some bluish, and some are black, and some start to be red. I still didn't grasp completely into this, but it's an interplay of refraction of or diffraction of light, and also the properties of the clouds and the wavelengths. So the shorter wavelengths penetrate easier, while longer wavelengths do not. So you have more dominant one or the other wavelength reflecting. So you can tell a lot about your product, a lot about the clouds, their thickness, their formation, through actually looking at the shadows, not only the shape of the shadow, but also the color of the shadow. Yeah, you can see this also here. You have some blue shadows. You have black and with some orange or dark red shades. Anyhow, last thing I will show you, maybe this same scene with a 500-meter resolution, where you again see better. Okay, it's not enhanced too much, but if we move forward in time, you start to see more photons hitting this top of the clouds and better structures. You even see the shadow of this uprising, overshooting top above the anvil. Yeah, the MTG is a long story, and we just started. Feel free to log into, or actually there is no login into Eumetview. It's readily available. You just type view.eumetsat.int and have fun with the data. The trick is to spend more time with it, and then you start to see things. So thank you for your attention, and thanks to other two presenters for an interesting briefing. If there are any questions, I'm here to answer.